So now we want to talk about L'Hopital's rule in the arithmetic forms and the power forms. Remember that there are 7 basic indeterminate forms. There are 2 basic forms right here. These are the forms that you can apply L'Hopital's rule to. So you apply L'Hopital's rule to those 2 forms and those 2 forms only. Now, what do you do for the others? For the others, you have to convert into this 0 divided by 0 or infinity divided by infinity form. We're going to see that converting 0 times infinity is actually quite simple. The infinity minus infinity is quite a bit more complicated, generally speaking, because you have to get a fraction, and there's not always a fraction. So you have to either create one or use the form of the functions in order to find one. And then the power forms, which are more difficult because the power forms have to be converted twice. First, they're converted into something of the form 0 times infinity, and then they're converted into the form 0 over 0 or infinity over infinity. So now we want to go ahead and we want to take a look at the arithmetic forms. So the arithmetic forms are the first 4, 0 over 0, infinity over infinity, 0 times infinity, and infinity minus infinity. So we're basically looking at the 2 arithmetic forms we haven't dealt with yet, 0 times infinity and infinity minus infinity. Now, in order to convert the 0 times infinity, what we're going to do is we're going to take advantage of the fact that multiplying by a number is the same as dividing by the reciprocal. So multiplying by something is the same as dividing by the reciprocal. So let's say you have some b and it's being multiplied by a. That's the same thing as b divided by the reciprocal of a, which is 1 over a. So multiplying by something is the same as dividing by the reciprocal. So what we do is we take either the representation that's giving us the 0 or the one that's giving us infinity, and we divide by the reciprocal of it. And that's going to fix the problem for us. All right. And you'll see how this works when we start doing some examples. So when you do that, it will convert it into either 0 over 0 or infinity over infinity. So multiplication by something is the same as division by the reciprocal. Now, in theory, it doesn't matter which one you pick to convert, but in practice, particularly when you have negative exponents involved, one conversion may be easier than another. So in theory, either way will work. In practice, one may be easier than the other. So we're going to start with this example here. We have the limit as x approaches 0 from the right of x times the cotangent of x. So again, remember that we are approaching from the right only so that the values are not allowed to be negative. And then we're going to be looking at what happens on the graph when we get to that point. Now, how many of you actually remember what cotangent looks like? Aha. So we have a little bit of a problem. If you don't know what cotangent looks like, you're going to have issues with it. So the first thing we're going to do is we're going to come over here and we're going to create cotangent of x just to remind you of what it looks like. All right. So when you're looking at the cotangent of x, notice what happens as it approaches 0 from the right side. Remember that cotangent is like tangent in that it has periodic vertical asymptotes. Unlike tangent, which is generally increasing, cotangent's generally decreasing, all right? So, and it's phase shifted from what tangent is. Tangent has vertical asymptotes at the multiples of pi over 2, the pi multiples of pi over 2, whereas cotangent has multiples, it has vertical tangents at multiples of pi, 0 and pi. So the pi multiples of that. So as you approach 0 from the right, trace your finger along the curve and notice it is going towards positive infinity. So that's what we mean by when you get to one where you can't actually plug it in because it doesn't exist, you need to look at the graph. And that's why you need to know what the graphs look like. So we're looking at the graph here. And so when we plug in 0 for x, we get 0, but the cotangent of 0 is undefined, which tells us to look at the graph. So that tells us that we have 0 times positive infinity. Now, when we get 0 times positive infinity, we need to think about which one we want to move in order to make it either 0 divided by 0 or infinity divided by infinity. Because I tend not to think in terms of cotangent, I'm more likely to want to move the cotangent because I know cotangent is 1 over tangent. So I could rewrite this one instead as the limit as x approaches 0 from the right of x divided by tangent of x. Now that seems like a simple thing. It is in fact the same thing as x divided by 1 over the cotangent of x, because 1 over the cotangent of x is tangent. So whichever way you do it, you need to get it in fraction form because our two basic forms are both fractions. So now that we have it in a fractional form, we need to reevaluate. Until you have one of those two basic forms, you cannot apply L'Hopital's rule. So we reevaluate here, and this gives me 0 divided by the tangent of 0, but tangent of 0 is defined and it's 0 over 0, which is one of our two basics. So since it's one of the two basic forms, then I can apply L'Hopital's rule at this point. So I apply L'Hopital's rule by putting L apostrophe H over the equals, and I take the ratio of the first derivatives of each factor. So the derivative of x is 1, and the derivative of tangent is secant squared of x. Once I do that, I would plug in again, but I tend not to think in terms of secant squared. So I'm going to go ahead and rewrite it again using cosine. So this is going to give me the limit as x approaches 0 from the right of cosine squared of x. Now I'm going to plug it in again. And remember that this means that you have the cosine of 0 quantity squared. Cosine of 0 is 1, so I have 1 squared, which leads to the result of 1, right? So our strategy is to get it into a fractional form, whether we divide by the reciprocal of one of the factors or whether we use the definition from trigonometry to convert one of them into a fraction. However we do it, it has to be in fractional form because our basic forms are 0 over 0 and infinity over infinity. Okay, let's take a look now at the next problem, which is number 12.
I have a question.
You have a question? Go for it, Juan.
Do we only have to put once the L apostrophe H?
Yes.
Like, or in
Yes.
every single, just once?
No.
Okay, great.
You only put L apostrophe H on the one time you take the derivative of the numerator and denominator. Right in front of that one. That's when you put it there. Okay. All right, let's take a look at our next one. Again, sometimes getting it into fractional form is very simple. You simply have to apply either a known property of a trigonometry thing or something about exponents. For example, in this problem, we have the limit as x goes to infinity of x squared times e to the negative x. Well, I have a negative exponent, which would naturally drop it to the denominator. So probably before I even plug in, I might drop it to the denominator, but I'm going to go ahead and plug it in first. This says x is going to infinity, so I don't have a number to plug in. And since I don't have a number, I need to think about the graph. So I'm thinking about the graph of x squared, which looks like this. And as x goes to the right, the y value goes up. So again, x is going to infinity, moving to the right, and the y value is going up forever. So we have infinity times, and now the second part, e to the negative x. E to the negative x is a decreasing exponential function. It comes down like that, and it approaches the x-axis. So as x moves to the right, this approaches 0. So we do have that indeterminate form, infinity times 0. It's not a fraction, got to have a fraction. So I'm going to rewrite it using properties for negative exponents instead of dividing by the reciprocal. And this is going to give me x squared divided by e to the x, right? Now, this is the same thing as dividing by the reciprocal. It gives you the same result. And now that I have this, I need to plug in again. I have to show that I have 0 over 0 or infinity over infinity. That's a grading point. So again, x squared is now going to lead to infinity in the numerator. E to the x, though, is not this graph. E to the x is a different graph where it comes up like this. And now again, as you're moving to the right, the y value goes to infinity. So I have infinity over infinity. But this is one of the two basic forms. So we haven't seen infinity over infinity as much as 0 over 0, but here it is. So we can apply L'Hopital's rule. We're going to write the L apostrophe H one time right here before the limit where we take the ratio of the derivatives. We are not doing quotient rule. All right, do not mistake this for the quotient rule. This is not the quotient rule. All right, the quotient rule would require f prime g minus g prime f all over g squared. We are not doing that. This is something different. Okay. All right. Let's now take a look and apply the derivative to each factor individually. I get 2x on top, and the derivative of e to the x is e to the x. So now I evaluate it again. The infinity is not a number I can plug in, so I have to think about the graphs. So I have to think about the graph of 2x. What does 2x look like? Well, 2x, when I graph it, goes through the origin and has slope 2. But again, as x goes to the right, the y value goes to infinity. So I have the form infinity on top. I still have e to the x, which is still approaching infinity on the bottom. So I have an indeterminate form again. So I'm going to apply L'Hopital's rule again. So I will write L apostrophe H again because I'm going to do the derivative again. Each time you take the derivative of the individual factors, you have to put the L apostrophe H. All right. So this time, when I take the derivative of the individual factors, I get 2 over e to the x. And then I want to plug in again. And I can think about the graphs. 2 is a constant. Now, if you want to think about 2, what they really mean is that it is the horizontal line y equal 2, which means it's always 2. The y value is not going up, the y value is not going down, it's staying constantly 2. But e to the x, that's still going to infinity. So we have a constant divided by infinity, which is going to go to what?
0.
0. So this gives us the result of 0. It's like I haven't talked much this morning. My throat's a little tickly. Okay. Next thing we want to take a look at is the next example. This one is a little bit more challenging. This is x times the sine of 1 over x. So this is an interesting example. If we want to look at it and see what it graphs like, we have x over sine of x. Graphing is a good way to see whether or not it meets your expectation. Right? So we have this sort of graph right here. And if you're wondering what that sort of wiggle there in the middle is, it's oscillating very rapidly as it approaches 0. Now it's not defined at 0 because if it were at 0, we'd have division by 0. So X cannot be 0. And what happens is it oscillates rapidly, but it looks like it's a damped oscillation, meaning that it looks like it's approaching some value. So our job is to prove through L'Hopital's rule that it is approaching some value, either as it goes to infinity or as it goes to 0. This particular one, we're looking at what happens as it goes to infinity. Well, looking at the graph, what do you think happens as it goes to infinity? Here's the thing, as X goes to infinity, it kind of looks like it's approaching a number. Does that make sense to everybody? Do you see how it's approaching the horizontal asymptote of 1? Not sure if that's going to be what we get, but let's try it and see. All right. So I looked at the graph, and on the graph, it looks like it wiggled a lot near the origin. And then it kind of bounced up, started increasing, and then leveled off and approached a horizontal asymptote of 1. So I'm expecting 1, but I'm going to look at it and see what I get when I do L'Hopital's rule. So first I evaluate. X is approaching infinity. So I have to think about the graph of X, which is a line. As X goes to infinity, the Y value goes to infinity. So I have infinity. And then I have the sine of 1 divided by infinity. Now, 1 divided by infinity isn't really a number, of course, but 1 divided by infinity would be driven down to 0, right? Because you have a constant on top and infinity on the bottom. So this would give us, writing, infinity times sine of 0, which is 0. So I have infinity times 0, which is one of the arithmetic indeterminate forms. Now I've got to get this written in terms of a fraction. And I will tell you that because of the fraction inside of the trig function, I'm kind of loath to mess with that. I don't want to mess with the sine. I like sine. I think in terms of sine, I kind of want to leave sine where it is, which means that I have to mess with the X factor that's by itself on the outside. So I'm going to, this time, there's no obvious way to do it. I can't use negative exponents. It is sine, and I don't want to write it in terms of cosecant. So I'm not going to use trig function definitions. So I am simply going to divide by the reciprocal. So I have the limit as X goes to infinity. I'm going to have the sine of 1 over X in the numerator. And I'm going to divide by the reciprocal of X, which is 1 over X. So when I'm looking at this, I've got this 1 over X, which is replacing this single X that you see right here. All right. So the 1 over X division by the reciprocal is the same as multiplying by X. Now I need to evaluate again. So I need to think about what this does. I know what sine of 1 over X is going to do. That's going to go to 0. So it looks to me like I have 0 on top. I have sine of 1 over infinity, which is sine of 0. Maybe I should create a little more space. I've got room. So I've got 0 on top still. In the denominator, I'm going to have 1 over infinity. Now, 1 over infinity, again, approaches 0. Or you can think about the graph of 1 over X. So when you think about the graph of 1 over X, the graph of 1 over X looks like this. Did I do that right? Nope. I have it upside down. I'm doing negative 1 over X. There we go. All right, so this is the graph of the reciprocal function 1 over X. And you can see that as X goes to infinity, the Y value approaches the X axis, so it goes to 0. Also, you can plug in 1 over infinity and see that it goes to 0. So now I have the indeterminate form 0 over 0, which is a basic. So I am allowed to apply L'Hopital's rule. So I'm going to apply L'Hopital's rule right here. So I get L apostrophe H, and I may need some more room on this one. And I'm going to take the derivative of the numerator, which is sine of 1 over x. It applies chain rule. So derivative of sine is cosine, freeze the inside, times, what's the derivative of 1 over x? You can go over to the
Negative
side. Yeah.
1x squared.
Yes. So you can think of it as x to the negative 1. So the derivative becomes negative x to the negative 2. So you can think of this as negative 1 over x squared. This is another one in addition to the square root that I actually recommend that you memorize. The derivative of 1 over x becomes negative 1 over x squared. It comes up a lot. It comes up a tremendous amount in calculus too. And so it does save you quite a bit of time if you've got that one memorized and you don't have to calculate it every time. Okay, so this is chain rule for the numerator. And in the denominator, we have 1 over x, but the derivative of 1 over x is negative 1 over x squared. All right, so the derivative of x to the negative 1 is negative x to the negative 2, which is negative 1 over x squared. Okay, so make sure you've got that. What happens with the negative 1 over x squareds?
They go to 0.
Yeah, they cancel, right?
Oh,
They cancel. We've got the same thing. So again, they cancel. Don't think about plugging in until you've done some algebra. In calculus, the general practice is do a little algebra to simplify at the beginning, then do some calculus, then do a lot more algebra to simplify, then do a little more calculus, then do a lot more algebra. So interspersed in every step should be some algebra simplification. It's kind of a balance between algebra, calculus, algebra, calculus, algebra, calculus. And of the two, the algebra actually takes up more space, generally speaking. So now we've got a rewritten limit as x goes to infinity of cosine of 1 over x. Now, we can go ahead and plug in again because we've done the algebra to simplify. So now we're going to do the calculus and we're going to substitute the value in again. And I'm thinking of infinity like a number, but I know it's not a number. So when I substitute this in, I get the cosine of 1 over infinity. Well, what would 1 over infinity approach? 0. Roz is correct. It goes to 0. Never quite gets there, but it gets close. And again, limits are what it looks like it's going to be, not what it actually is. So this gives us cosine of 0, and the cosine of 0 is 1. So our final result is 1, which based on the graph is exactly what we see here. So if we were to graph the line y equals 1 and make it a dashed line, you would see that it is approaching that horizontal asymptote as it moves off to the right. Okay. Let's talk about converting infinity minus infinity. This is one of the more tricky ones, the more difficult ones. There are a couple of basic strategies that we can do. We can try multiplying by the conjugate of something with a square root divided by itself. That will make it into a fraction. But sometimes we don't have a square root and we don't need a conjugate pattern. When we don't need the conjugate pattern, what we typically do is we just artificially impose a fractional form on it. So we'll multiply by either 1 over x over 1 over x or 1 over x squared over 1 over x squared. So if there are trig functions involved, you can see whether or not rewriting them in terms of sine and cosine might give you a fractional form and then get a common denominator. All right, remember, you've got to have one fraction. You can't have two terms, and that's the problem with infinity minus infinity. You have two different terms, and you need one term that's a fraction. So you're going to either multiply or divide by something, or you're going to rewrite the trig forms so that you can get a common denominator. If all else fails, multiply by 1 over x over 1 over x, or 1 over x squared over 1 over x squared. Now, multiplying by either one of these is allowed because they're both forms of 1. That will give a common denominator of either 1 over x or 1 over x squared, right? And then there may be some reduction that will happen. So these are the basic strategies, these 3 strategies for converting 2 different terms of form infinity minus infinity into one term that's a fraction. Now remember, the problem with infinity minus infinity is that there are different sizes of infinity, different magnitudes, all right? So we actually call them, we name the sizes of infinity using, well, gosh, I don't know. Is it Hebrew? Aleph. I'm not sure. Anyway, I don't remember what kind of letter Aleph is. It's not Greek. I think it's Hebrew. So Aleph. Aleph naught, or Aleph sub 0, is the smallest size of infinity. Then Aleph 1 is the next magnitude. Aleph 2, Aleph 3, Aleph 4. You can keep going from there. So there are different sizes of magnitude of infinity. For example, the number of rational numbers is the lowest form of infinity. The number of rational numbers, that would be ratio of 2 integers, which includes all the integers and the counting numbers. That is Aleph naught, size of infinity. They're countable, right? That you can set up a pattern and you can count the rational numbers. Now it goes forever because it's an infinite group, but there is a one-to-one correspondence and you can count them. On the other hand, the irrationals are not countable. There's no way to count them. There are so many of them that you can't set up a one-to-one correspondence. So there is, in some sense, another level of infinity, more of irrational numbers than there are rational numbers. So the irrational numbers are uncountable, which is a larger infinite set than the rational numbers, which are countable. Okay, let's take a look at example 14. In example 14, we have the limit as x goes to infinity of x minus the square root of x squared plus 1, the quantity. So when we look at this one, we want to imagine what we could do. One thing that we did in chapter 2 was we multiplied by the conjugate divided by itself. That's still a decent strategy that you could try. What we're going to do now is we're going to try a slightly different strategy. We're going to use strategy 3, which is to artificially impose a fraction form on it by multiplying this by 1 over x over 1 over x. That will give us a common denominator. So we're going to take that and we're going to multiply by 1 over x over 1 over x. Actually, let me back up. What is the first thing that we should have done? Always.
Check.
We should check and see what form we have. We should substitute the value that x is approaching in and see what we've got. So when I look at this, I have x approaching infinity. X is a line, right? It's the identity function, slope 1. As x goes to the right, the y value goes to infinity. So I have infinity minus. Now, the square root's a little bit more difficult, but remember that square roots basically look like this, all right? Upper arm of a right opening parabola. And when I'm looking at it, x squared is always positive, so I don't have to worry about negatives, which I really don't have to worry about anyway, because I'm approaching positive infinity. So I'm so far to the right that the negatives are long gone. So I've got x squared plus 1 under this radical. So this is also going to grow to infinity slowly, more slowly than x, but it will go to infinity. So I have infinity minus infinity. Now here's the issue. If they're roughly the same size of infinity, and they are, then it could stop at any finite real number. If they're different sizes of infinity, it's either going to get pulled towards positive infinity if that's the larger one, or towards negative infinity if that's the larger one. Now, why do I think they're roughly the same size? I think that they're roughly the same size because they're both algebraic functions. In other words, they're both adding, subtracting, multiplying, dividing, raising to powers, or taking roots. That's algebra. Multiply, divide, add, subtract, raise to powers, take roots. That's algebraic. I don't have a mixture of natural log with algebraic. Those are different types of functions. I don't have exponential with algebraic. Those are different types of functions. So when I'm looking at it, I'm looking to see what kinds of functions they are, and these are both algebraic. So I think they're roughly the same magnitude. So I don't know where it's going to come to a stop. So I'm going to artificially impose a fraction form by multiplying each of them by 1 over x over 1 over x. So the first thing that I'm going to get, and I'm going to take my time in writing this one out so that I don't lose anybody. Square root of x squared plus 1 times 1 over x over 1 times 1 over x. So does everybody see that I am going to end up with the common denominator of 1 over x? Right? Since I have a common denominator artificially imposed, I can combine them together. Now this is all algebra. So I did one step of calculus, which is checking what it approached, infinity minus infinity. And now I've got to do a lot of algebra to get it in a better format before I do L'Hopital's rule. So x times 1 over x gives me 1 minus, and then I have this radical x squared plus 1 divided by x, all divided by 1 over x. And I forgot my limit. X is going to infinity. All right? So I have the limit of this expression right here, and I want to see what I can do to it in order to simplify it some more. So for example, I'd like to get rid of this square root of x squared plus 1 over x. So I know, because x is approaching infinity, that at some point all the x values are positive. So I can assume that x is positive. And that means that if I want to slide the denominator x up into the radical, I can think of it as x squared. So I'm still doing algebra. So this is another step of algebra. So now I have the square root of x squared plus 1 over x squared over 1 over x, still algebra. I need to clean that step up. Now I've got two terms on top, x squared plus 1 divided by x squared. So it's a binomial divided by a monomial. So I can split it into two fractions. And again, I'm taking my time with this one and really stretching it out. I would probably do fewer steps if I were doing it by myself, but I don't want to lose anybody. Still doing algebra. Little bit of calculus, whole lot of algebra. All right, repeat. Okay, so now the next thing I want to do is reduce. I've got x squared over x squared, which becomes 1. So I've got the limit as x goes to infinity of 1 minus the square root of 1 plus 1 over x squared, all under the radical, over 1 over x. Now, how do you know to stop? Experience. And experience is just code for having done lots of problems, seen lots of examples. You go until you can't think of anything else that would make it simpler. Everything you do would make it more complicated. Then don't do those things. So I've got this about as simple as I can get it now. So I want to reevaluate. I need to do some more calculus. So I'm going to plug in the value of infinity. I now have one fractional form. So I have 1 minus the square root of 1 minus 1 divided by infinity, all divided by 1 divided by infinity. All right, now let's think about what that does. So when I've got 1 divided by infinity, I know that that's going to approach 0. It doesn't ever get to 0 because infinity is not a number. I can't plug in infinity, but I can think about what it approaches. So this is going to go to 0, and this is going to go to 0. So I get 1 minus the square root of 1 over 0, which is 1 minus 1 over 0, which is 0 over 0. That's one of my 2 basic indeterminate forms. Since I have a basic indeterminate form, then I can go ahead and apply L'Hopital's rule. So when I apply L'Hopital's rule, I'm going to have to apply it to this form right here, which looks, well, pretty awful, more or less. Yeah, looks pretty awful, but we don't have a choice. So I'm going to copy, I'm not going to copy. I'm going to copy by hand. All right, so we've got equals L apostrophe H. So again, L'Hopital's rule is not taking the derivative of the quotient. It's taking the ratio and saying if they're differentiable, and they are at infinity, then the tangent lines are good approximations to the function. So the ratio of the functions has to be equal to the ratio of the tangent lines. And so we're taking the ratio of the tangent lines, which is the derivatives. Derivative of 1 is 0 minus derivative of a square root is 1 over 2 the square root. All right, 1 over 2 the square root. And then we have to apply chain rule. Chain rule is the derivative of what was under the radical. So times, under the radical, I had 1, which derivative is 0, plus 1 over x squared. X squared, I can think of 1 over x squared, I can think of as x to the negative 2. So the derivative of x to the negative 2 is negative 2x to the negative 3, or negative 2 over x cubed. Right? I don't quite have enough space here. It would be better if I had a lot more room to work. So I'm going to create some space below. All right? So this is going to be multiplied by negative 2 over x cubed. Now, that's just the derivative of the numerator. So we found the tangent line approximation to f, and now we need to find the tangent line approximation to g. But g is 1 over x, which is one I said you need to memorize, and it's just negative 1 over x squared. Okay. So let me see if I can just copy this to the next page. See if it got it all. Yep, it's all there. Okay, so I have this limit, and I need to now do, you got it, a lot of algebra. So a little bit of calculus, a whole lot of algebra, a little bit of calculus, a whole lot of algebra. That's the process. So I've got in the numerator a negative times a negative, which is going to make it positive. I've got 2 in the numerator and 2 in the denominator of the numerator, so the 2's cancel. And I've got 1 over x cubed, the square root of 1 plus 1 over x squared. Okay, and then in the denominator, I've still got the negative for the denominator, and it's 1 over x squared. Now we want to undo the division by the reciprocal and make it multiplication by the factor. So if dividing by 1 over x squared is the same as multiplying by negative x squared. So I'm going to move what is in the bottom of the bottom or denominator of the denominator to the numerator, which is where it goes. So I get 1 over x cubed square root of 1 plus 1 over x squared times negative x squared over 1. Now the x squared and the x cubed will reduce. And I get the limit as x goes to infinity of negative 1 over x square root of 1 plus 1 over x squared. Everybody with me so far? Have I lost anyone? This is some really, really complicated algebra here. I told you these infinity minus infinity forms, they're pretty tricky. And this is the worst possible. So if you're thinking, God, this is hard, this is the worst case, right? You know, I always pick the hardest examples I can find to work in class so that you have an easier time on the homework, or I try to. Now we've done some algebra. I've simplified it as much as I think I can. So I'm going to try to substitute the value in again. I have x approaching infinity. So when I do that, I'm going to have a negative 1 over infinity times the square root of 1 plus 1 over infinity squared. Now, infinity squared is still infinity. It's just bigger. And so 1 over infinity squared is going to go to 0. And again, it's approaching 0. So this becomes negative 1 over infinity times the square root of 1, which becomes negative 1 over infinity. You have infinity in the denominator, and you have a constant in the numerator. And because you have a constant divided by infinity, it's going to drive it towards 0. In fact, it's going to drive it towards 0 from below. So it's going to be coming up towards the x-axis from below. So this is going to approach 0.
So I have a question. I forgot on one of the steps we were doing the derivative of the numerator, and for some reason I'm not connecting the dots on taking the derivative of that square root value.
Okay, so when you take the derivative of 1 right here, you get 0. And remember, the derivative of a square root is 1 divided by 2 times the square root, frees the inside. So the inside doesn't change. All right? This is the rule. 1 over 2 the square root of u, where u doesn't change at all. So we still have 1 plus 1 over x squared. And then we multiply by the derivative of what was under the radical. So the derivative of 1 is 0, but the derivative of 1 over x squared, I wrote it as x to the negative 2. And the derivative of x to the negative 2 is a negative 2x to the negative 3, which is negative 2 over x cubed.
Can you remind me what the difference is? So I would look at that square root quantity as like that quantity to the 1/2 power. Why is this different?
It is that. It is. It's the same thing.
But if I did that, it would seem more straightforward. I'd just like bring 1/2 to the front, freeze the inside, and then go from there.
But then you'd have a negative 1/2 power, which would drop it to the denominator. You can, it's the same thing. You'll get the same result. If you like the fractional exponents better, use the fractional exponents.
Okay.
That's fine. Okay, we have one more example to do before we get into the power forms. And this is 1 over x minus 1 divided by sine of x. So in this one, we need to have a common denominator. We can try various things. The trig function that we have is already written in terms of sine, so there's no obvious way to get a common denominator. If I had tangent or secant, I could write them in terms of sine and cosine and see if I could get a common denominator that way. I could multiply by 1 over x over 1 over x. That's a possibility. I would choose 1 over x because this one is 1 over x. If this was 1 over x squared, then I'd multiply by 1 over x squared over 1 over x squared. That's a decent one. Or you can just look at it and go, well, gosh, that's simple enough. I know the common denominator is x times sine of x. I can get a common denominator and just combine them into a fraction. So that's the strategy we're going to take here. So we're going to go ahead and we're going to take the limit as x approaches 0 from the right, because we can't get to 0 because it would be undefined on both functions. And we're going to take the 1 over x and we're going to multiply by sine of x over sine of x minus 1 over sine of x, and we're going to multiply that one by x over x.
Don't we want to substitute first and check and then?
Oh, yes, I forgot. Thanks, Michael. I keep forgetting because I'm getting ahead of myself because I know they are that form. All right, first we check. So we have 1 over 0 minus 1 over sine of 0, which is, well, wait a minute. What happens when your top is a constant and your bottom is approaching 0? Where does it go? To infinity. Yeah. So we have infinity. And then again, I'm going to get 1 over 0 for the second one, which again is known. This is not indeterminate. It's known. It goes to infinity. So we have that infinity minus infinity form. Thanks for the reminder. Always check first. Make sure you have an indeterminate form. Can you apply L'Hopital's rule if you don't have an indeterminate form?
No.
No.
No, you cannot. Don't try. In fact, what two forms do you have to apply L'Hopital's rule? There's only
0
two.
over 0 and infinity over infinity.
That's correct. 0 over 0 and infinity over infinity. Any one of the other 5 forms has to be transformed to one of those two. So we're trying to transform it by getting a common denominator. So I've got the limit as x approaches 0 from the right. I've got now sine x over x sine x minus x over x sine x, which is a common denominator. So I can write it together. And again, I'm taking more steps than I would by myself because I don't want to lose anybody. Now I would put parentheses around the x or the sine x just to emphasize that that minus x is not a part of the argument of the trig function. You need to make sure it doesn't creep up on there. Okay, so I look at it and the first thing I do is I say, all right, I'm doing algebra. Is there more algebra I can do to simplify it? I would look for a common factor of x, but sine of x does not have one. Don't you dare ever, ever, ever cancel part of the argument of a trig function. Never, ever, ever, all right? Anything past the trig function is staying, all right? So you cannot cancel it. So, and the second term, negative x, doesn't have a sine x, so I don't have anything to cancel. I can't think of anything else algebraic to do, so let's substitute in again. So when I substitute in, I get the sine of 0 minus 0 over 0 times the sine of 0. The sine of 0 is 0. So I get 0 minus 0 over 0 times 0, which is 0 over 0. That is one of the 2 basic indeterminate forms where I can use L'Hopital's rule. So now I'm going to find the ratio of the tangent line approximations. So I'm going to look at the numerator and say, is that a differentiable function? Sine x is differentiable everywhere, x is differentiable everywhere. The product of differentiable functions is differentiable. So I can go ahead and use the tangent line approximations. So this is the step where we are using L'Hopital's rule. So derivative of sine is cosine. Derivative of x is 1. In the denominator, I have to apply the product rule. Now, I've graded your exams, and I noticed that several of you are messing up the product rule. So we need to review the product rule coming out of section 3.3. So remember, the product rule is f prime g plus g prime f, where I've got a multiplication between x and sine x. There's no multiplication inside the trig function. That's not sine times x. That's sine of x. And that of is not multiplication. Of is not always multiplication. So derivative of x is 1 times sine x, f prime g, plus derivative of sine x is cosine x times x. Now I'm going to rewrite this, lest that x get wrapped up somehow inside the argument to cosine, which is a danger. So we have cosine of x minus 1, or you might write it as -1 plus cosine of x, sine of x plus x cosine of x, right? So I applied L'Hopital's rule, and I've done a little bit of algebra to simplify. What should my next step be?
Plug in again.
Try plugging in again and see if you have a value. So when I plug in this time, when I substitute it in, I'm going to get the cosine of 0 minus 1 divided by the sine of 0 plus 0 times the cosine of 0. Now cosine of 0 is 1, so I have 1 minus 1. Sine of 0 is 0 plus 0 times 1, which is 0 over 0 plus 0, which is 0 over 0. It is again that one of the two basic indeterminate forms. So I'm going to apply L'Hopital's rule again. So when I apply L'Hopital's rule again, I didn't say it would be easy or short. I'm going to apply it to this form right here. So I'm going to be taking the limit as x approaches 0 from the right. The derivative of cosine is going to be negative sine of x. The derivative of the -1 is 0. The derivative of sine x is cosine x. And then I have to use the product rule on x times cosine x again, because I've got multiplication right there with the dot. So the derivative of x is 1 times cosine of x. And then the derivative of cosine of x is negative sine of x times x. Now I'm going to rewrite this, and I'm going to move the x at the back in front of the sine x so it doesn't get inside of that trig function by accident. So I have negative sine x divided by, well, I've got 2 cosine of x's, right? Cosine x plus cosine x, so that's 2 cosine x. And then I've got minus x sine of x. And I've simplified as much as I can, so I think I should substitute in again. So I try substituting in again. So I get negative the sine of 0 divided by 2 times the cosine of 0 minus 0 times the sine of 0. Sine of 0 is 0, so I have negative 0. Cosine of 0 is 1, so I have 2 times 1 minus 0 times 0, which is 0 over 2, which is 0, which is the final result.
This is the end of our discussion of the arithmetic forms for L'Hopital's rule. In the next video, we're going to be taking a look at the power forms.